Hello, and thank you for joining us for Microgrids and Hybrid Power Everywhere, optimizing the new energy wave. My name is Tricia Fitzpatrick, and I'm the Marketing Manager at Homer Energy by UL. A quick housekeeping note before we begin: if you don't have audio, go to the Audio tab on the Webinar Control panel. Click on the phone bubble, and then click back on the computer bubble, and that often cures the audio problem. We have you all muted, so please send in your questions via the question area of your webinar control panel. You can type them there as you think of them, and we will get to as many questions as possible at the end of the session. This webinar is being recorded, and all registrants will be sent a link to the recording when it is available. I do want to extend a special thank you to Comb App for sponsoring today's webinar. Comb App makes the Intelisys hybrid control, which provides microgrid control solutions to monitor and manage all sources of energy, including solar, wind, battery energy storage, and generator sets. It's suited for off-grid and grid-connected applications. And after the webinar, please do stop by their website and learn more at www.comap-control.com. Before we begin, I want to quickly talk about Homer software. Homer is an acronym for Hybrid Optimization of Multiple Energy Resources. It has been a key piece of making the microgrid market possible. And the Homer approach includes three processes nested together. At its core, Homer is a simulation engine. It simulates the operation of an electric power system for 1 year in time intervals of hour by hour or minute by minute. At each time step, Homer looks for the most cost-effective way to meet the electric load. Simulation tells you how one system operates, and then the optimization step simulates hundreds of different systems to find the least cost solution. Homer also offers sensitivity analyses, which allows you to look at the impact on system design and system costs of changes in variables that you don't have control over, such as fuel price or wind speed. Homer software does have several versions to serve the range of distributed energy systems. Homer Pro is our original product, and it has broad applications for microgrids that are islanded or connected to unreliable grids. Homer Grid was designed for behind-the-meter, grid-connected systems where demand charge reduction, time of use rates, incentives, resiliency, and reliability matter most. And we just introduced Homer Front plus UL analysis, which is for front-of-the-meter, utility-scale hybrid power systems. This capability combines Homer front-of-the-meter modeling software with the analysis of UL experts to help energy developers optimize and evaluate the profitability of utility-scale solar, wind, and storage systems. And now for today's presentation, please welcome Homer Energy founder, Dr. Peter Lilienthal. In his presentation, he will examine the significant transition that is sweeping the energy landscape as energy suppliers seek resiliency and look toward reducing carbon output and lowering cost by using microgrids and hybrid power systems that run on clean, renewable energy resources. As a leader and pioneer in the microgrid industry, Dr. Lilienthal is uniquely qualified to present today's topic. He has been at the forefront of the microgrid industry for nearly 30 years and has experienced and driven the adoption of microgrids and now hybrid power. He received a Ph.D. in management science and engineering from Stanford University and joined the Solar Energy Research Institute in 1990, which became NREL. He went on to become a senior economist at NREL and created Homer there. He then founded Homer Energy in 2009, along with Dr. Marilyn Walker, to commercialize and further enhance Homer software. In 2019, UL acquired Homer Energy. He is now UL's global microgrid lead, and Dr. Walker is UL's global hybrid power systems lead. Now, I will turn the presentation over to Peter.
Thank you, Tricia. As many of you know, Homer Energy has now been part of UL Renewables for over a year. UL Renewables has a huge global presence with over 500 renewable energy experts operating in 140 countries. It has provided advisory services and forecasting to hundreds of utility-scale projects. In addition, the Homer software has been used to evaluate over 100,000 hybrid projects. These have been mostly distributed energy projects, but we are now in the final stages of testing a new version of Homer for utility-scale front-of-the-meter projects. We are so proud to be part of UL that I feel compelled to talk a little bit about their history. They were founded over a century ago in 1894 when electricity was still a new concept and Chicago's World's Fair wanted to show off this novel technology but needed someone to certify that it was safe. Since then, they have been the preeminent safety certification body in North America and certified the first solar collector back in 1980. For the past 10 years, they've expanded their focus on safety to include sustainability and acquired the German Wind Energy Institute, DEWI, in 2012, and AWS True Power in 2016, and now Homer Energy in 2019. I created the first version of Homer at the National Renewable Energy Lab back in 1992, and it has been continuously updated ever since then. Homer Energy was created as a private company with the exclusive license to commercialize and enhance Homer in 2009. Our two big new product releases were Homer Pro in 2014 and Homer Grid in 2018. And now we are announcing a new analysis service using Homer Front software for utility-scale front-of-the-meter projects. The title of this webinar is Microgrids and Hybrid Power Everywhere. What do we mean by everywhere? Well, the global nature of the energy transition has always been in the forefront of our approach. We used to even use the byline clean power everywhere. In the beginning, we focused on remote systems where the alternative was expensive diesel power. This is where hybrid systems were first cost effective. These were mostly small village systems, but also islands, some of which are tens or hundreds of megawatts. They don't have to be geographic islands, just electrical islands, like the Alaskan village in the top picture here. These applications are all over the planet. But now we really mean everywhere, including places that rely on more conventional energies like coal, natural gas, and nuclear. The rapid decline in the cost of photovoltaics has really helped as the sun shines everywhere. But the real revolution came from what is happening with lithium batteries. That is being driven by the electric vehicle industry, but the power industry is a major beneficiary of the rapid decrease in cost, increase in performance, and especially the massive increase in manufacturing scale. Storage is important because solar and wind don't stand on their own. They need to be part of a hybrid system that includes storage, and batteries are a cleaner form of energy storage than a tank of fuel. By everywhere, we don't just mean geographically, but all kinds of individual facilities. Hybrid systems have an important role to play behind the meter at any facility that needs to be resilient and have reliable power. The only way to guarantee truly high reliability is to put the power source at the site where the power is needed. Otherwise, you're vulnerable to all kinds of disturbances in the distribution system. These behind-the-meter distributed power systems are now cost-effective enough to also be valuable simply controlling energy costs, particularly demand charges. I want to talk about the full range of hybrid systems, from tiny solar home systems for developing countries to continental-scale grids. I've created this chart that is kind of busy. It is just based on my experience on how the state-of-the-art in hybrid systems has evolved over the last 30 years. The vertical axis is the percentage of renewable energy on a power system, and the horizontal axis is a logarithmic scale of the system size. Small systems, like solar home systems in developing countries on the right side of the chart, have in many ways been the leaders because they have always been 100% renewable. But in the beginning, they were the only systems that were. Back in the 1990s, the large central grids had only token amounts of wind and solar. But there were interesting hybrid mini-grid and microgrid projects on islanded systems. The colored lines on this graph show that change is accelerating, which is necessary if we're going to get to zero carbon by 2050. You can see that change is accelerating because the lines are getting further apart. As solar panels have gotten bigger and batteries have gotten better, the 100% renewable systems have also gotten bigger, but they're still very small systems. The large utility systems in North America, Europe, China, and Japan have also increased their renewable penetration, but are still at relatively low percentages on a total annual energy production level. Why have the small systems been able to be 100% renewable? The main reason is that an individual household can be more flexible about its demand than a whole community or country. As we'll see later, flexible demand is really valuable. But also, innovation is always easier in small systems, and battery integration is one such innovation. Creating stable AC power without rotating equipment like a conventional generator requires power electronics, which was a new field and not available at large power capacities. There have been great improvements in power electronics, but there's still more work to be done to scale them up to the largest power systems. I mentioned the Alaskan experience earlier because that is where a lot of the early experience with hybrids occurred. Solar was still expensive, but there are scores of Alaskan villages that have an excellent wind resource and are completely dependent on diesel power. This picture is from St. Paul, Alaska. They developed a wind diesel system there almost 25 years ago. Because batteries were definitely the weak link back then, they designed the system to completely avoid the use of batteries by flexibly supplying excess power to a thermal storage facility heating community buildings. They have been able to run 100% renewable with no operating diesels for weeks at a time, relying just on the flexible demand to provide stable frequency and voltage. There are other Alaskan villages that have distributed thermal storage in individual homes that are controlled by a wireless network throughout the village. As the wind varies with gusts and lulls, the power to these heaters varies seamlessly and in real time. This is the kind of innovation that a small system can prove out before deploying in a large system. More commonly, we used to see renewable diesel hybrids that avoided the use of batteries by running in a fuel saver mode, where the renewables simply reduce the loading on the diesels. This saved some fuels, but actually made the diesels run less efficiently and created maintenance issues. Several companies developed special modifications to diesel generators to reduce these problems, but these kinds of systems could never run diesel off. They're just a stepping stone to a high renewable penetration. There have been a lot of announcements of goals to get to 100% by 2050 or sooner. This is a huge challenge. We need to define it. People throw the term net zero around a lot. Originally, it just meant that if you had enough solar panels on your house and you exported as much power back to the utility as you purchased from them, then you were net zero. You were using the utility as a big loss-free battery, but the system wasn't net zero. Now, it's sometimes used to mean capturing and storing enough carbon to offset all of our carbon emissions. Although the fossil industry is betting billions on carbon capture, the only proven technology is photosynthesis to grow biomass like trees. Although this is part of the solution, 100% renewable would get us to zero carbon without carbon capture and storage. We're clearly headed in that direction, but there are challenges that need to be overcome. The first is just the sheer scale of deployment. The battery industry is scaling up dramatically, and so are the solar and wind industries. So this is possible, but they will need to become absolutely huge industries. A second challenge becomes obvious when you do the kind of optimization modeling that we have always been doing at Homer Energy by UL. To have enough energy production during periods of low resources, you need either a huge storage capability or a huge renewable capability, or both. This will be much larger than you need during periods of high resources. These resources are too capital intensive to sit idle much of the time. This means that from an economic perspective, you have overbuilt those capabilities. A better approach is to build flexibility into the system. Instead of the flexibility of fuel-fired generation, you will need flexible demand. What makes this challenging is that unlike the household systems, we need to communicate to many different users who will have dramatically different reliability requirements. Some applications like pool heating can be extremely flexible. Others, like high-tech manufacturing, can't tolerate any deviations in power quality at all. This requires a completely different way to think about the communication and control requirements of the power system. Fortunately, the technology exists, so this is not a technical challenge, but it is a huge regulatory challenge. And regulatory change is slow and contentious. And that is frankly my biggest worry about achieving zero carbon. A saving grace is that electric vehicles may be the solution. We built the capability to model flexible demand into Homer Energy over 20 years ago, and have now built an EV module into Homer Grid. In Homer Pro, the flexible application is usually water pumping, but now there's an enormous potential for flexible demand for EV charging. The graph on the right shows how much the cost of power can come down if it is acceptable for a small amount of demand to not be met right when it is demanded. Electric vehicles are such a potentially huge electric demand that a relatively small percentage of the charging load could give the system the flexibility that it needs. For example, if 20% of the vehicle miles traveled was in an electric vehicle and 25% of that charging was controlled, that equals to 5% of the energy used just in light vehicles would be flexible. This is equal to 1% of today's total electricity consumption. As the graph shows, just 1% could have a big impact. There are lots of caveats to this oversimplified analysis. First of all, it was done for a small system. Also, today's electricity consumption will grow dramatically with EVs. Finally, and most importantly, the controlled charging has to be made up later, which this simple graph ignores. The point is not in the specific numbers, but in the scale of the potential. If a significant portion of transportation has onboard batteries, and a significant portion of those batteries are charged in a managed way, it could provide the flexibility that the power system needs to approach zero carbon. The last conclusion demonstrates the power of optimization modeling. The Homer software products have several optimization algorithms embedded within them. The graph on the right shows Homer zeroing in on the system with the least cost combination of capital costs on the horizontal axis and operating costs on the vertical axis. It is doing that automatically using our proprietary optimization algorithm. This clearly is useful for identifying least cost solutions and deciding on the best project design. It is also what you need to avoid bad ideas, and there are a lot of those out there. So you shouldn't just accept a design that some system vendor developed using their own rules of thumb. You can also compare proposals because different vendors will always have different design options. But there's another great value to optimization modeling. Hybrid design involves many degrees of freedom. There are a lot of design parameters with substantial trade-offs between them. For example, you can reduce fuel consumption by increasing the battery size, or the PV size, or both. But there are diminishing returns as you do that. Where to stop and what is the best ratio of battery to PV size is often far from intuitive. Unlike many optimization programs, the Homer software doesn't just give you the single best solution, but lets you look at simulation results for all of the system designs it considered. This is how you get real visibility into the trade-offs. And there may be very good reasons for picking a system that was not the very least cost. Another value of optimization modeling is technology analysis. There are a lot of new technologies under development. Do they make sense? At what price point would they make sense? In what application? Some technologies are a great fit in one application and horrible fits in another application. Or you might want to know how much carbon pricing would help, or better financing. These are all questions that you cannot answer without an optimization model that considers all the design possibilities and the trade-offs between them. Finally, I'm not the only one saying that electric storage changed everything. But I like my graph that shows that change is accelerating and that small systems are leading the way to 100% renewable systems. Even though they are small, we can learn a lot from those small systems. Personally, I love my electric vehicle, but more importantly, EVs are motivating the massive expansion of the battery industry. What is often overlooked is just how revolutionary they can be in terms of adding the flexibility of the power system that will be needed to get to high penetrations of renewable energy. And as long as the regulatory system can adapt fast enough, this will be possible. Finally, optimization modeling is the key to understanding all of the design trade-offs that will be necessary to both design good systems, but also to make this transition to clean power everywhere. And with that, I will hand this back over to Tricia.
Thank you, Peter, for that excellent presentation. Before we go to questions, I want to address one question that often comes up, which is, how do I get started? There are several ways you can utilize UL's expertise. You can use Homer software to model your microgrid and find the least cost solution. You can download our Homer Pro or Homer Grid software for a free trial at homerenergy.com. And to help you dive deeper into the program, we offer online training. Or you can bring one of our engineers into your project to help you do the modeling or do the modeling for you. You can contact support at homerenergy.com. If you would like help with the full scope of your project or want to know more about Homerfront plus UL analysis, please contact Renewable Energy Services at ul.com. So now let's go ahead and go to questions. So thank you so much for that wonderful presentation. Marilyn Walker has been collecting questions for us. And they are now sharing their webcams. So if we could please go ahead and go to questions now.
Great, thanks. Sure, so a couple really practical questions, maybe not totally related to your talk, Peter, but I think it's an interesting question is, what steps would need to be taken to adapt to flexible demand? Is this regulation or are there technical steps?
Well, there's both. There's technical steps, like I mentioned, about communication and control. So when does the system need that flexibility? That would need to be communicated to the to all the users. So the technology clearly exists in terms of the internet, and but the control of that is a software challenge, and it's clearly possible, but it's kind of a large software project to develop a reliable system that communicates with millions of individual systems. There is an alternative to that. I'm not sure the regulatory and bodies and the utilities would be comfortable with it, but everybody sees the same frequency at the same time within a grid. So like if there's a disturbance in Maine, the folks in Louisiana are seeing the same frequency disturbance. So if the frequency, so it could just be autonomous, operating off of the frequency that the device sees. There's a bunch of issues with that. And utilities kind of like to have some control, not have things just happening automatically out there. Although that is what happens with demand today. So I think that's a promising potential solution, but it needs a lot more research than just me saying it's an interesting idea. On the regulatory side, though, you have to compensate the users for the providing that flexibility. So that's a rate hearing, and there's a whole variety of different ways you might do that in terms of well, how often are they allowed to? Is the utility allowed to call on you to provide that flexibility, for example, or and for how long? And depending on the application, like something operating off a thermostat, it could, you wouldn't mind if the temperature in your room or your refrigerator, for that matter, varied a little bit for a little while, but not for a huge amount of time. So there's all kinds of issues about how much warning do people get, how long would that you'd be called upon to provide that flexibility, et cetera, et cetera. And that all has to go through a regulatory process. So I think that's the bigger challenge than the technical challenge.
Great, thank you. Here's a great question that I love because I think it relates to Homer Energy's hometown of Boulder. What are the primary benefits? Actually, I'm going to put it into a two-part question. One is, could you describe some of these small 100% renewable? Actually, yeah, could you describe some of these small 100% renewable systems? And then, kind of related, could you talk about the primary benefits available to local communities by enabling their network to become an on-demand microgrid? So maybe talk about the smaller systems and then
Yeah, okay.
transition into local microgrids for larger
Okay.
communities.
Okay. Well, those really are two, I think, if I understand correctly, pretty separate questions. But let me answer the first one first. Those small 100% systems, they're tiny. For a long time, and we call them solar home systems in the sort of development community and energy access community. They're just a single solar panel with a battery and hopefully a charge controller. Sometimes they don't have charge controllers, so the batteries don't last very long, which is a problem. But they're super simple. Or solar lanterns, which it's all one unit. But we're talking about the solar lanterns are in like the 5 to 10 kilowatt range. And the solar home systems used to be 50 watts. So you have a 50-watt panel, which is, maybe slightly larger than a laptop in size. Now you can get panels that are several hundred kilowatts, several hundred watts. So those 100% renewable systems are getting larger. You're even seeing some mini grids that's serving multiple households that are 100% renewable. The households have to get along together, because they have to mutually agree on how to manage the battery and what to do during a cloudy period. But in that 1 to 5 kilowatt range, backup generators are kind of a pain. And then you have to worry about fuel and you have to worry about maintenance. And if you don't need it, if the idea is, well, the battery is going to be good enough, except maybe a few times a year, why go through all that hassle just for a few times a year if you can coordinate with your neighbors properly? So you're starting to see systems in the few kilowatt range that are 100% renewable. But this is developing country stuff mostly, and it's tiny. It's a couple of kilowatts at the most. So that's one. Now on the local control issue, the issue is, and I think it's more of an issue in California actually, where they're going to do these preventative safety shutoffs. I'm probably not saying that quite right, but where you want to, there's a whole variety of reasons why you might want to island yourself from the larger grid. So in California, it's because the larger grid is going to shut you off anyway for preventative safety reasons because of potential wildfires. In developing countries, the reliability is really poor, and you might want better reliability, or the voltage stability is bad, or for whatever reason you want to separate yourself from the grid. And if you have an automatic transfer switch, it's a totally different kind of power electronics you need for a grid forming inverter versus a grid following inverter. So if you're always connected to the grid, the inverter just needs to follow the grid in terms of frequency control. But if it's islanded, it needs to create its own stable frequency, totally doable in the range up to a couple of megawatts. It's not something you can do at the 100 megawatt level yet, but it's different and it's slightly more expensive. So I think I answered that question. I don't remember it exactly, but hopefully that answered the question.
Great, thanks. Thanks. Yeah, I'll take one. I'll give you a break for a second, Peter, because this one always comes up. It says, I'm an Italian engineering student. Do you believe that blockchain technology is an advantage in managing the energy trading of a microgrid? Yep, absolutely. So if you're a student out there and you're interested in blockchain and energy trading, A lot more research and work is needed on that before it's going to come. But absolutely, I think blockchain is already happening. Many utilities are writing their own blockchain. So I think that's a great project for students. Gosh, lots of questions coming in. Okay, here's an easy, maybe a simple one. When you talk about renewable penetration, are you talking about energy or power capacity?
In that graph, I was talking about energy capacity. There are so many different ways to measure renewable penetration, and actually, one of the output screens in Homer lists 8 different ways of measuring it, penetration. So when people throw around numbers like, "Oh, this is 40% renewable," or it can be really confusing. So I'm trying to make a point of saying it was annual energy penetration. You know, I see a question in here. Can I just grab one, Marilyn? Do you mind? About the challenge EVs provide to the distribution system, and especially fast charging. Actually, we have an electric vehicle and we just plug it into a 110 volt outlet because we don't drive that far. But the people want to charge these things in 15 minutes or something, which means massive amounts of power are going through that cable connecting the car to the charger. You know, they're talking about 500 kilowatts, or, you know, that's probably on the high end, but 150 kilowatts. That's way more than typical convenience store or gas stations distribution, you know, connection to the distribution system can allow. So that's a huge problem. So one of the things that Homer Grid can do when it models electric vehicles is say, okay, well, we've got a limit on our connection to the grid, and what's the economics of having a battery at the charging station so that we can pull power from the grid at a low power, but then inject power into the car at a much higher power level. Interesting application. I know there's some companies out there developing technology to do that, developing charging stations that do that. They're more expensive, but they're going to save on upgrading the distribution system. So it's a really interesting economic question, and something that Homer Grid can handle. So Marilyn, next question.
Okay, sorry. Could you describe, so you talked about actually this accelerating, how change is accelerating. And could you talk about what is leading the accelerating change, and what else might, you know, what would be good things to happen to accelerate the change that maybe aren't happening?
Well, there are several things that are happening all at once. On the technology side, photovoltaics have just gotten a lot cheaper, so up until that happened, wind was pretty cost effective if you had a good wind resource, and there are plenty of places with good wind resources, but not everywhere. But the sun shines everywhere, and I always like this analogy that, and I don't mean any disrespect to the wind industry here, but with wind is really sensitive to the resource. So one side of a hill from the other side of the hill can be the difference factor of 10 or more in terms of how much power you'll get out of a wind turbine. And there are places that just simply don't have enough wind at all. And the output of a wind turbine is proportional to the cube of the wind speed. So that's very nonlinear, very sensitive. With photovoltaics, it's sort of linear with the resource. And sure, some places are cloudy and some places are sunny, but it's not as big the difference, and the difference doesn't vary in that kind of dramatic way over small areas. So there's less resource uncertainty. I like to say, roughly speaking, you know, Phoenix is the sunniest city in the country, and Seattle is the cloudiest city in the country. And the difference in output of the same PV panel in those two places is a factor of 2, which is, you know, not small, but it's way less than I would have thought intuitively. So when solar became cost effective, that kind of changed everything, because you can deploy it anywhere. I mean, Germany was a big leader. It's not quite as cloudy as Seattle, but it's right up there. But northern Germany, especially, is not a sunny place. So and they've got and they're a leader. So solar can be applied anywhere. It's gotten a lot cheaper. That was the first thing that happened. On the technical side, like I said, the batteries are making all the difference in the world in terms of getting to higher penetrations. The other thing is just greater awareness of the value of this, the need to promote renewable energy. The U.S. has been kind of a laggard on accepting the climate challenge, but it's changing here, and it's certainly changed much more dramatically in Europe and other places. And so that's just growing awareness that we need to do this, and policy. So it's a combination of policy and economics and technology all coming together, and I just see that happening, and obviously policy makes a big difference. So we just think that's going to continue to accelerate.
Great. So this is a related question then. You know, how far, I'd like you to talk about, well, actually, I'm just going to read the question. What do you think, you know, how much renewable penetration of a large grid is possible without large scale batteries, and how far can we go until we need large and expensive amounts of batteries?
Well, first of all, you know, I've been focusing on solar and wind. Hydro and geothermal don't have that problem. They are rotating equipment. They're using turbines, and so the big challenge of inertia and reliance on power electronics doesn't apply to hydro and geothermal. So you have places like Iceland, which has a huge geothermal resource. They're not limited. And there's other places, Costa Rica comes to mind, Norway, that have huge hydro resources. So that's a whole different issue, and they can go to high penetrations today without a problem. But if you don't have those resources, then it's kind of unclear, because what the limit is, and it really varies whether you're talking about solar or wind, because you know, solar just is in the daytime, wind can be 24 hours, but then solar doesn't have 3-day lulls, but wind can have multi-day lulls. So, but depends on the wind resource, so it really varies a lot from place to place. I remember back in the 90s when there's a lot of utility resistance to this, and we were just trying, and I was still at NREL. We were trying to say, well, gosh, you can do 5%. You don't have to worry if it's 5% renewables. You don't have to worry about this. And well, it turns out you can blow past 5%. It's not a problem. 10%. And it also depends how you're measuring the percentage, which goes to that earlier question of what does renewable penetration mean. That's a difficult question to answer. The truth is, batteries have gotten so cheap now that I don't think the question matters anymore, because it's no longer a big problem to start installing batteries, and it's happening. They're putting in battery installations of 100 megawatts are going in. It's very, very dramatic how fast battery deployments are starting to happen in the 100 megawatt scale. We never actually found that limit, I don't think. And like I said, it's very site specific, very specific to the particular system. We never really found the limit, and now we'll probably won't find the limit, because we're going to start putting in batteries.
Great. Okay, there's a couple of Homer questions that I think are worth talking about. Let's see, the new ones coming in. Are there any new modules? What's the plan for Homer? What's coming up modules, additions, improvements? What are we
Well,
working on?
I mentioned the electric vehicle module. That's came out a few months ago, so that's new and exciting, I think. But what we've been working on a lot lately, and it's sort of in beta testing at the moment. It's not really quite ready to just give it out to everybody, but we are looking for beta testers, and we're calling it Homer Front for front of the meter systems, meaning utility scale systems that aren't that don't have a native load. They're not behind the meter at an energy using facility. They're just a power plant like any other power plant, wind farm or solar park, which obviously there are a lot of them around in the world now. But what's the change is, and where Homer really comes in, is when they're hybrids. Like Homer stands for hybrid optimization of multiple energy resources. So if it's just a wind farm or solar park, there's no battery, fine. But now, like I said, you're starting to see these battery installations all the time, and it's that trend is going to accelerate. So we've created a new version, Homer Front, for these utility scale hybrid systems like solar plus storage, wind plus storage, solar plus wind, whatever. We're looking for beta testers. We're working with some large developers right now, a few to, and now that we're part of UL, it's a great opportunity for us, because before we were acquired by UL, we really didn't do that much consulting and advisory work. We were focused on the software. But UL Advisory has a huge advisory capability all over the world, especially North America, but really all over the world. And so even though it's in beta testing, our advisors are using it already on advisory projects to help developers and independent power producers, et cetera, look at hybridizing a solar park or wind farm. And this is not a simple problem. Batteries are complicated. I've been touting how great they've become and everything, but they're really unlike any other utility asset. They have charging constraints and discharging constraints and lifetime issues, and knowing when to discharge involves actually thinking ahead a bit, and knowing when to charge and discharge, and it all depends on your electric rates or your prices. And the contracts are complicated. In California, has something called a resource adequacy. Other places call it a capacity market, where you get paid, but you have to prove that you're available, which means you can't discharge whenever you want necessarily. It's a complicated analytic problem, but we've created the software for it, and we've got the advisories capabilities to help people with that. That's our most exciting new thing, really, and huge potential for these utility scale solar plus storage systems.
Actually, another one that, and I think it speaks to other questions that we've had on here, is yes, vehicle to grid. So we have questions absolutely like electric vehicles are this enormous hit onto the grid, and vehicle to grid is one of the ways of making that more of a win-win. I'm going to use the non-technical term there. Peter could probably fix that for me if he needs to, but that is something that we're looking into. The Homer Front work has kind of overtaken our small team right now, but absolutely the electric vehicle charging infrastructure was our just step one of approaching this, and looking at how electric vehicles work with behind the meter grid systems is going to be another thing that we are going to put into Homer for sure. Okay, let's see.
If I can say something about vehicle to grid,
Yeah.
I was still at NREL back in like 2005, and we were talking about vehicle to grid back then, and it was considered kind of a crazy idea. But I could see the potential for it. There's again, power electronics issues, those are totally solvable. There's regulatory issues, they're contentious. But the objection that I got was, well, EV owners are going to be protective about their batteries. You're not going to want to let the utility discharge your battery. Now, if you were adequately compensated for it, that's a different story, and that's back to the regulatory issue. But one of the values that I saw for vehicle to grid was just spinning reserve, just reserve capacity for emergencies. The utilities spend, it costs the utilities a lot of money to have that reserve capacity available in case a big unit goes down. You know, the Texas issue is a perfect example. And it doesn't happen very often. But they spend a lot of money having that capability for emergencies. And because if a big unit goes down, it's a big problem for the utilities, and they have to really hustle to replace that very, very quickly. So the spinning reserve wouldn't hurt the batteries because it just wouldn't get used very much, but it has real value. So I always thought that was an overlooked value for vehicle to grid. But first, we have to get a significant number of EVs out there before it's worth going through the whole regulatory issue.
Okay, thanks. So we have two questions that I'm going to try to merge into one. And one of them is just asking about how Homer manages ROI and what Homer does with ROI. And the second one is about plans to add additional economic or finance tools into Homer.
So the first question is not very specific. We do calculate return on investment, or internal rate of return is a little more explicit, specific metric. And we use the classic, I mean, it's a well-trodden, it's a well-defined term, internal rate of return, because we calculate the future operating and maintenance costs, future fuel costs, if there are any, replacement costs. There's a terminal value issue, and we calculate that. We unfortunately call that salvage value. That's probably not the best term for the terminal value at the end of the project life. But so we use the standard textbook definition of internal rate of return. We are adding more finance capability to Homer, things like debt terms and capital structures, capital debt equity ratios, etc. That's in the works. Like Marilyn said earlier, we've been really focused on getting a Homer front out. That this kind of finance capability is more important for those larger projects. So that's definitely on our roadmap. One of the things that is built right into Homer front now is a little more disaggregation on the costs. Like in Homer Pro and Homer Grid, we just say, well, what's the capital cost? Well, the capital cost is actually made up of many components, from the equipment, the purchasing, shipping, insurance, et cetera. So with Homer front, we'll be able to disaggregate those capital costs. So in Homer Pro and Homer Grid, it's more of an economic model than a financial model. But with Homer front, we're adding more of that kind of financial detail.
Okay. All right. I think these are related questions. I'm getting a few Homer front questions. You've got people interested. Is there a minimum size for Homer front? And yeah, I think that's fundamentally the question. I think there may be some confusion here about front of the meter versus how fundamentally different adding storage is to utility scale projects versus behind the meter. But could you talk about size?
Well, the software doesn't have a minimum size, but the utilities do. So the utilities aren't going to contract with an IPP um, for a tiny project, and so and every utility is going to feel a little differently about that. But um, if it's front of the meter, meaning it's not serving a facilities load, it's just selling power to the utility company, and that's all it's doing. Um, uh, the software doesn't care if you want to model a small system, but the utilities will care. So there is a sort of a natural lower limit to that. Marilyn, it felt like there was a second part to that question, and what was that? Was there a second part to that question?
No, I think I do think that you answered it, because as I looked at the question, it's really different. Right, selling power to a utility versus actually creating an independent hybrid, independent.
Yeah. Oh yeah.
On-demand.
There was something else I wanted to say, which is the big difference is there's no native load. You're just selling power to the utility. With Homer Pro and Homer Grid, you're meeting a load at the site. It's a distributed energy resource. That comes first, and you may be selling excess power to the utility, but the Homer Front doesn't have a facility load there, and it's selling power under a contract typically or into a market, whereas Homer Pro and Homer Grid have like tariff structures that are fixed as opposed to real-time price. Well, they can use real-time prices, but typically not. So that's the difference. It's a wholesale transaction with the utility and there's no facility load.
Hi, so excuse me, I just wanted to let you know there's time for probably one more question.
Yep, thanks. That's exactly what I was planning. And we're getting lots of questions about Homer, which is great. And is there any plan to add heat pumps or heat storage into Homer?
Plans to. Well, it is on our roadmap. It's not. We've been asked about thermal storage for a long time, and obviously heat pumps have become well, they've been around for a long time, but suddenly with this interest in 100% renewable and getting natural gas, stop using natural gas for heating, they've become much more interest. Unfortunately, I have to say there's no immediate plan for that, but it is on our roadmap. When we are going to be hiring some new software developers, so we could take some applications for that if you want. And so we should be able to accelerate our roadmap, but I'm not going to give a time frame for that. I'd love to have those in Homer, but we've got there's many things on our roadmap.
Right. Thank you. Okay, I do want to say I'm getting lots of questions on here about sales. How do I buy Homer? It's wonderful. How do I try Homer? So homerenergy.com, right up there on the screen there, sales support they can help you with all of those questions. And we have a great team there ready. So with that, I thank you, Peter, and turn it back over to Tricia.
Well, thank you both, Marilyn and Peter, for that excellent discussion. And thank you to the audience for your excellent questions. It's the best part of webinars. And before we go, I did just want to let you know what is coming up in April. We have a presentation where we're joining forces with PEER, which is a rating system that evaluates a power system's performance. PEER is working to transform the power sector just as LEED transformed the building sector. And we'll look at how Homer helps, your project's value before you build it. And the PEER evaluation system shows how well you have met your objectives. And that's going to be April 29th at 9 a.m. Mountain Daylight Time. So please be sure to sign up to receive notifications at microgridnews.com. And also, we'll be announcing the call for speakers very soon for the 9th annual Homer Conference that will be in October. So be sure to sign up to stay connected at microgridnews.com. I just want to thank you again for attending today's webinar. If you did not get your question answered, as Marilyn suggested, you can send it in through your sales rep or our support desk, and we'll respond to it. And watch for an email in a few days with the recording of this webinar. And we hope to see you at our next event. Thank you.